Good evening, students. Welcome for the Standard 10 CBSE extra classes. Sorry for the delay. There was some issue with the joining link. That's why. This session is mainly for the CBSE revision. Okay, because we want all of you to wait a minute. Okay. So this is purely on the CBSE for your school exam, for your how to attend your school exam, because ours is little higher than the CBSE board. So we thought that we will do questions only to help you for the school test and the school exam. Okay. Rajeswari ma'am will be taking the class. Okay. She will be joining shortly. Still then, can you, Aishwarya is with us for handling the session. Your mentor only, one of your mentor only. Okay. Aishwarya, shall we send a poll? How many have completed the number system? Can you send a poll? How many of you have completed number system?
Hello.
Hello.
Hello, I'm here.
Yeah, ma'am, add your board.
Yeah, I have added. Can you see my board?
No,
Is my board seen?
you are not shared it.
No, ma'am.
I've done it.
Yeah.
Is it okay now?
Yes.
Okay.
Yes. Sorry, students, for the delay.
Yeah,
With the
sorry, there
start,
was a small
Rajeshri ma'am.
Yeah, there was a small technical problem which I had to resolve. And good evening, students. Sorry for the delay. Okay. Now we will start with the number system. That is today's first class of class 10. See, we all know the formation of numbers. For every number, if you add one, you'll get the next number and so on. And from every number, if you minus one, you get the previous number. So with this concept, we have been developing our number system, which is always, there is no limit for the numbers. And now here, you have to get reminded of the division algorithm, which you have studied in your earlier class. So in your earlier class, you have I'll study the quotient into divisor gives you the reminder. Okay. So the same thing we are going to study in a different form, and this particular form has been structured and formulated, and we call this as Euclid division lemma after its inventor. Okay. Any number can be written in the form of quotient into divisor plus reminder. So this is the particular form. That is what we are going to elaborate now in this session. And we will be also going through how a number, a prime, what is the difference between a prime number, composite number, and how a composite number can be factorized. So these are all the different items that you are going to see. And using this fundamental theorem of arithmetic and Euclid's division lemma, how are we going to find the LCM, that is the lowest common multiple, and also the highest common factor of 2 or 3 numbers, that we are going to see, and also the decimal representation of rational number. So these are the session objectives. Now let us begin one by one. Okay. Now, see any number, for example, you take 6. Now, if you divide 6 by 1, what do you get? You will get 6 into 1. And then there is a remainder 0. So you will be adding this. Similarly, 6 we are going to divide by 2 6. So what are you going to do? 6 you have to divide by 2. So on dividing you will get 3 as the quotient and 2 as the divisor. So you will be writing this as 3 into 2 plus the remainder 0. Suppose 60 is going to divided by 3 say. So you will be writing 2 as the quotient, isn't it? So 2 into 3 times it divides, plus again the remainder is 0. Now what will happen if you divide 6 by 4? Even then the 4 is dividing 6 only one time, and then 6 minus 4 you will get 2 as the remainder. Okay. So this is a very, very basic uh, question, that is basic understanding based on division lemma, that is division algorithm. If you are dividing 6 by 5, so that gives you 5 into only one time will be able to divide, and you will get 1 as the remainder. If you are going to divide 6 by 6, you will get 6 into only 1, and you will get 0 as the remainder. So this is what you are going to see when you are. So this is a very, very basic property. Now here there is a question may come all of you. Listen. Suppose if you are dividing 6 by a bigger number, say. So strictly speaking, by concept is we cannot divide a smaller number by a bigger number. 6 we are dividing by 7, say. Yes, we can still say that it can be divided by 0 times, isn't it? So 0 times, if you are dividing 7 into 0, and again we will get 6 as the remainder. Okay. So this is one basic thing that we have to. So this not only applies to 7, it can be even a bigger number than 7, maybe 6, maybe 7, maybe 8, maybe 9, any number can be divided by another number, provided we have to choose the correct remainder, find the remainder correctly, and then write. So this way, if you try with any number, so I have just made it simple by taking the number 6. We can try with any number, maybe 126, 124, maybe 10, and then maybe 12, or any number 11, any number you can take. It can be written as a multiplication product of one number plus a suitable remainder, whichever will come in that case. Okay, so that way we can always rewrite a number. Okay, this is the fundamental principle of division algorithm, which is taken as a statement called Euclid's division lemma. UCLID, Euclid's division lemma. Lemma means a proven statement. Algorithm is an observed truth, that we can call it as lemma, and this is called division lemma. And we write here any number A can be written as a product of two numbers. So B into the B is here the divisor, and then we are dividing by Q times, that is the quotient, plus another remainder. We can try this for any integer. Okay. So A can be an integer, B is an integer, Q is an integer, R is an integer. But this R is chosen to be less than B. When you are writing is in this form, the R can take the values 0, 1, 2, etc., etc. It can take up to the value of B. So this is called Euclid's division lemma. Okay. So this, in what way it is going to help us in finding the LCM and HCF, we are going to see elaborately in this class. So before that, I just wanted to ask you, now are you okay with my board? Are you all able to see my board? Are you okay with my board? Are you all able to see that? Is my board okay? Kindly message me. Okay. Now let us see what is the next process theorem. Theorem we cannot say. Next property about the prime and composite numbers we all have to once again revisit. So the numbers, you all know what is a prime number. Your earlier class understanding says that the numbers which have only the factors as one and the same number, one and the same number are called the prime numbers. For example, we can quote the numbers 2, 3, 5, 7, etc. There are about 25 prime numbers up to 100. And then we can even find the numbers beyond 100. There we can always find out more prime numbers. Okay. Now, composite numbers are numbers so which have factors other than one and the same number. Okay. There are so many composite numbers. Any number we can always test by testing whether what all the factors it has got. Say for example, you take 1 is neither prime nor composite. Okay. So 1 leave alone 1. Now take 2, it can have only one factor. Okay. Now take 3, it can also have only one factor and the same number itself. Now take the number 4. 4 has factors 1 and 2 and every number, the same number is a factor. Okay. So it has got 3 factors. Therefore, 4 is categorized as composite number. Similarly, we can find innumerable numbers which are composite. Okay, this is a very, very earlier and basic a fact that we have studied in your earlier classes. Now, here you take any composite number for that matter. Say, for example, let us take 12 is a composite number. Okay, so a composite number can be written as a product of prime numbers. That is the fact. So 12 we can write as 4 into 3. 4 we can write as 2 into 2. And then again, if you multiply by 3, you will get 12. Here there are 2 and 3 both are prime numbers. So we can write 2 as 2 square into 3, which is equal to 12. Okay. So this is 2 is a prime number, 3 is a prime number. Now I'll give you one more example. Let us take the number 30. What can we say? Can you suggest some number? 35. So 35 is a prime number which we can write as 7 and 5. So into 1 of course, and there is a number 35 also. Okay. So 7 into 5 into 1 gives you 35. Now take the number 24. If you take the number 24, you can write this as 6 into 4, and then the 6 can be factorized as 3 into 2, and then the 4 can be factorized as 2 into 2. Therefore, I can write 24 is equal to, there are 3 powers for 2, so 2 power 3 into 3 power 1. So there are, it's written as a product of prime numbers. So this is a very, very basic fact that every composite number can be factorized in and written in the form of a product of prime numbers. Okay. This also you should once again revisit before learning further. Okay. So this we call as the fundamental theorem of arithmetic. Fundamental theorem of arithmetic. So the Euclid's division lemma and fundamental theorem of arithmetic, they both are not very new to you. Only thing is we are giving a special name and structure to the theory, and then it has been followed for finding the HCF and LCM of numbers. Okay. Now once again we will go back to the again one more earlier concept, HCF. Okay. What is the expansion of HCF? It is the highest common factor. Okay. That is, when we say common, that means there are more than one number involved. For example, you take 4 and 10 say. So you all know 4 is nothing but 2 into 2. That is 2 is a factor for this. And then for 10 it is 2 and 5. So 2 is a factor, 5 is a factor. If you consider both the numbers, there is 1, 2 which is common for both the numbers. Therefore we say that, and it is the highest of all the common factors. So we call this as 2 is the HCF of the two numbers 4 and 10. Two numbers 4 and 10. Okay. Are you understanding this? Are you understanding? Now here we will be moving. There are so many methods of finding the HCF. That is, by the fundamental principles, we will be factorizing the numbers involved, and then we will be listing out the common factors, and out of that we will be choosing the highest common factors. This is what we have done in your earlier class. And then there is again one more method called the continued division method. Say for example, the same example 4 and 10, we are going to find the HCF means. So what is the smaller number? 4 is going to divide the bigger number 10. It can divide 2 times and the remainder is 2. And now this remainder is going to divide this number 4. So it can divide by only 2 times. 2 twos are 4. So therefore, the particular divisor which makes this division with a 0 remainder is chosen to be the HCF of the two numbers 4 and 10, and we still write 2 is the HCF of the two numbers 4 and 10. Okay, this we call as continued division method for finding the HCF of two numbers, and then this is nothing but applying the lemma principle of, that is Euclid's division lemma principle. We can rewrite the same statement as 10 is equal to, by 4, choosing 4 as the divisor, it can divide 2 times and then there is a remainder of 2. Now this 4 is going to be divided by this number. Therefore we write 4 is equal to 2 is going to divide this by 2 times and then the remainder is 2, and this particular division gives you the HCF. So for which the remainder is 0, therefore the divisor is chosen to be the HCF of the two numbers 2 and 4 and 10. Okay. Now, therefore, when we write using this division lemma, that is A is equal to BQ plus R, we choose the B as the divisor and Q should be the quotient, and then the remainder is chosen like that. So this format is to be maintained, for which the number is going to be, the numbers are A, and then B is the divisor, Q is the quotient. So the divisor is written in this form only as a first number in the product. So that we have to understand. Okay. Now, next is, how are we going to find the LCM and HCF using prime factorization method? So prime factorization method also we can use for finding the LCM of two numbers. And also there is a long L division method which you have studied in your earlier classes. But just because you are introduced to the two new concepts, so it is advisable to use this particular method which I am going to elaborate to find the LCM and HCF of two numbers. Okay, this method you are supposed to follow that. Now here, suppose we are find the LCM of, I am going to find the LCM of, say about 9 and 15 say. So find the LCM is the question. Okay. Now here we can write 9 as 3 into 3. So therefore we can write 3 square into 1. Now how do we write 15? 15 we can write as 3 into 5 into 1. If you look at the prime factorization of both these numbers, it is like this 3 square into 1 and 3 into 5 into 1. Okay. Now out of this, the highest power for the variable 3, sorry, for the prime number 3. Therefore, when we are choosing the LCM, the number with the highest power is first chosen. So I will write here LCM is equal to 3 square, and then here the 5 is not it is not repeated here, but still 5 is there. So we have to include that 5 also, otherwise the common multiple will not come properly. So 5 I am taking. So then it is 3 square is 9, and then 9 into 5, 45 is the LCM of these two numbers. Are you understanding? So this is how you should choose the LCM for the two numbers 9 and 15. Now using this, we can find a HCF also. How do you find HCF? Here it has got two powers of 3, and here there is only one power of 3 which is common for both. Therefore I write HCF is equal to 3. So this is how one prime factorization we will be able to find out both HCF and the LCM. So you have to be thorough with finding the prime factorization of the given numbers. Okay, this is one thing. Now second, we'll be continuing with the same kind of one more concept is also you are taught here, that is introduced to you in this class. Now you all know every rational number can be written as a decimal form, that is rational number. You can quote some rational number, say 2 by 3 is a rational number, 1 by 2 is a rational number, 1 by 4 is a rational number, 1 by 8 is also a rational number, etc. etc. Any rational number you can choose, and that can be written as Jyotsana Baisani has asked, how do you identify whether a number is prime or composite? Okay, 1 second. So when you see, you ask, how do you identify whether a number is a prime number? Okay, I am coming to your questions one by one. So now rational number 2 by 3 means the number 3 is to divide 2. Okay, so we all have know the fact that it is not, because it's a bigger number, it's a smaller number, we are not going to get a whole number as the answer. Okay, therefore we can't divide, you are just putting a 0. 0 times only it can divide, and keep a point here and proceed, and then with a 0, and you will get 18, and it is going to be continued like this. You will get 0.6666, etc. Okay, this is one type of decimal representation of 2 by 3. And then again 1 by 2 if you take, and then you will get 2, and then here 2 is going to divide 1. You put a 0 here, and then you put 0.5. So this is one type of decimal representation. Okay. So I'm coming to your questions. Okay. There are some one or two questions have come. I will tell you one by one. Okay. First, let me finish this and then go to the both your queries. Okay. So like that, there are several type of decimals. So here I have introduced two types of decimals, 0.6666, etc. and then 0.5. What is the difference between these two decimals? Can you tell me? The 0.5, when you write like this, the decimal just terminates. We cannot expand it further. We call it as the terminating decimal. It is a terminating decimal. That is, with that we cannot extend it any further. It just gets over. And then similarly, if you take the decimal point 0.6666 etc., the number 6 is repeated infinite number of times, and we rewrite this as 0.6 with a bar on top. This notation means the number is going to be repeated for infinite number of times, and we call this as non-terminating repeating decimal. It is called non-terminating repeating or recurrent. Both the words you can use. Non-terminating repeating decimal. Okay. Now, in addition to that, there is one more type of decimal numbers which is neither non-terminating, it is non-terminating and also non-repeating. For example, about that you would have studied in your earlier class 6, 4, 2, and then it goes on like this for infinite number of places. We can't predict what is the next number you're going to come. Here we can predict, but here we cannot predict. It is just extending up to infinite number of places. And this decimals we call as non-terminating, non-repeating decimals. And now about which you would have studied in your earlier class. And then these numbers we have classified as the irrational numbers, and then we have found out that this cannot be represented as a fraction. Therefore, they are irrational numbers, non-terminating, non-repeating. I am not going to elaborate on this particular concept in this class, but anyway, you have to remember these facts. That's enough. Non-terminating, non-repeating. And my question is, when are you going to get such decimal numbers, especially when you find the square root of non-perfect squares? For example, root 2, root 3, and then root 5, and then root 7. If you all take these numbers, even root 6 also, they are all non-perfect squares. If you attempt to find the square roots, we will come across this decimals, and then this decimals we call as so this numbers we call it as non-terminating, the non-repeating decimals, and we call them as irrational numbers. Okay. Now coming to your questions one by one. So the first question asked here is, how do you identify whether a number is prime or composite for a bigger number? See, every even number ends in 0, 4, 2, 6, 8. We all know, therefore they all have factors 2. So we can say that the number is having a factor 2 or 3, divisibility test. And then sum of the digits if you find out, and then if it is divisible by 3, it is divisible, it has got 3 as a factor. And then the units and tens place digit you should see, and then whether it is divisible by 4. So we have to just check using your divisibility test whether the numbers have got factors. Okay. So that eliminates. Now once the composite factors are over, we can try the numbers, prime number factors like 7, like 13, like 11, like 19, like 17, and then 23, like that you should keep on trying. And then if sometime it clicks, then we can say the number is a composite number. If it is not able to click up to that half of the number, you should try. For example, 101 you take. You can try the 50 numbers. So 101 is neither a factor of 2, it doesn't have factor 2, it doesn't have factor 3, it doesn't have factor 4, it doesn't have factor 5, it doesn't have factor 6, and then it is not even having a factor of 7 and 8, 11 like that, and we can conclude that it is a prime number. Up to 50 you try whatever number, it is not clicking. 33 if you try, and 33 3 times, again it is not a factor. 11 it is not a factor. Okay. 1 plus 1, 2, 2 minus 1, 0. It is not a factor, it doesn't have factor as 11. Then it try for the prime numbers. It's only by trial and error method. We should keep trying whether it is using divisibility test and then trial and error method. We should find out whether it is a prime number or not. Okay, this is one thing that you have to find out. And then what is the proper definition? Okay, the composite number can be resolved into prime factors and written as a product of primes. Every composite number can be resolved into prime factors and be written as a product of primes. This is the proper definition of fundamental theorem of arithmetic. Now, what is the remainder when 3 into 129? 3 into 129, we are going to divide by 13. So this number, it's a very, very ordinary step only, 387. So now we can find out 387, I am going to divide by 13, say. 387 is going to be divided by 13. So we can write this as so if you can do it by mind, okay. Otherwise, we can have a small rough work here and then write here it is 2 times 30, 26, then 12, and then here 7, 9 times. So 9 times is 117. So it is 10. So we can write 387 as it is 13 divisor first and 29 times and then plus remainder we can write like this. Okay. Now next question, how to know? The same question is repeated by one more person. If Euclid's, can the remainder be considered as a negative value? So in the Euclid's division lemma, it is about the positive integers. We cannot consider the negative remainder. Okay. So when we write the numbers, A is great. When you write a particular A is equal to BQ plus R is a positive number greater than 0, greater than or equal to 0. And then B is a number which is greater than 0. And Q is going to be greater than 0. A is also going to be greater than 0. Okay. So we have to 0. That is, we can write this as 0. R is a number which is lying between 0 and B. It can take the value 0, it can take the value 1, 2, 3, but it is going to be less than B. So we have to write like that. Okay. 0 is less than R, less than or equal to this R, but R is going to be less than B. This is how you should rewrite the statement. Okay. Again, Niyasri, the same question I have answered. How to find whether we have to break it into prime factors by trial and error method using your divisibility test. So divisibility test, normally we will be knowing about 2, 3, 5, 9, these are all standard. And suppose if we have to test a prime number, for example, we have to test for a number whether it is divisible by 15, means 5 and 3. If it is divisible by 5 and 3, it is divisible by 15. So like that, we have to resolve that particular divisor into prime factors and test whether it is a factor, both the factors for these numbers. Okay. This is the way we have to find out whether a given number is prime or composite. Okay, this is how you should do it. Now, coming back to your decimal representation of rational numbers, I have already told you about the 3 different decimals. There is one more fact. The fact is, if the denominator of a rational number can be factorized as, so with factors, prime factors as 2, 5, and powers of 2 and 5, nothing else. So if that is the case, then the decimal expansion is terminating. Okay, the terminating. Now, in addition to 2 and 5, the denominator of the rational number has one more prime factor. Okay, then the decimal is non-terminating. In order to understand this sentence, so you just consider the example. 2 divided by or 3 divided by 10. If you take this as, and then we can using fundamental theorem of arithmetic, the 10 can be factorized as 5 into 2, and then there are only two factors, 5 and 2. Therefore, we are going to have a terminating decimal expansion. So it is going to be 0.3. And now, for you take another number, 3 by, what we can say, 3 by, okay, or I'll give you another example, 2 by 15. So if you take 2 by 15, take the denominator, it is nothing but 2 by 5 into 3. So it is either 2 or 5 or both, or in addition to that there is one more prime number as a factor, then it is non-terminating decimal expansion. So a few more examples also we can consider. You take the number 5 by 14. So if you take the denominator, it can be factorized as 2 into 7. Therefore, we have 5 divided by 2 into 7. So it has got 2 as a factor. So it is not only 2, there is an addition, there is one more prime factor, namely 7. This is non-terminating. Suppose if you have got the one more, I'll give you this example. 8 divided by 105. A simple question is it going to have a terminating or a non-terminating decimal expansion? So we have to factorize this 105. So 105 is nothing but, it is 3 into 5 into 7. Okay. So 3 into 5. So 5 is alone okay. But in addition to that, it has got two more prime factors, 3 and 7. Therefore, it is not divisible. It is not, sorry, it is having a non-terminating decimal expansion. Okay. Now here, I will give you another example. You take 6 by 70. Okay. 6 by 70 can be reduced as 3 by 35. So let us have 9 by 70. So 9 by 70 we can have. So 70 we can take it as, if you resolve it into prime factors, it is 2 into 5 into 7. So by rule 2 and 5 are there. Therefore, no problem. But there is, in addition to that, there is 7 also. Therefore, it is going to have a non-terminating decimal expansion. Okay. This is how you should conclude, and we will be making use of this for solving some problems, which we'll be doing it at the end of this session. So let us go back to the questions now. The first question here is, the HCF of 2895 and also divide 171. The first question is 2895 and 171. Okay. Now here these two numbers we should find the HCF. So there are two ways of doing it. I've already told you. We had to resolve in prime factors. Now here advised to do it by using division lemma only. So now this 171 has to be divided. So I have to write 2895 is going to be divided by 171. And we don't know how many times it's going to divide. For that, we can do a small rough work. Nothing wrong. Okay, if you divide and find the quotient as 16, quotient as 16, many of you have found out, and then the remainder is 12. So the next step is what? How are we going to divide this? Sorry, the 159 is the remainder. So 171. So here the next step is, here 171. This divisor is going to be divided by this remainder. So I can write this as, this is 159 multiplied by 1. Obviously 12 is the remainder. Okay. If you are not very thorough with this divisions, you can do a rough work and find out how many number of times it can be divided. So next rule is what? Your 159 is going to be divided by this 12. So 159 is equal to 12 into 13 times is 156, and then 3 is the remainder. Next, this 12 is going to be divided by this 3. So I write this 3 into 4 times it divides, and the remainder is 0. The particular divisor which gives the remainder 0 is going to be the LCM. And of course, many of you have written it. And for those people who have got the answer as 1 and 12, kindly recheck your calculations. Okay. So 12 cannot be, because the division has to continue. The remainder is 3 here. So it has to continue. That is why it is continued division. And finally, we get the remainder as 0. That is the HCF. Okay, very good. Now, let us move on to the second question. The second question is, find the factors of 7429. So it is, we have to find out what are the factors for this number. So what I have told you, you try with 2 not responding, try with 3 not responding, try with 4 not responding, 5 obviously not a factor, then 3 and 2 are not there, means 6 is not a factor, and then here 7 is not a factor. For 7 also there are some divisibility procedure. If you find it is little too tough, just you can do actually work out and see whether 7 is a factor or not. And then 8, it is not a factor. You have to take the hundreds, tens and ones. It is not a factor. And obviously 9 is not a factor. Again, sum of the digits is not a multiple of 9. So it is 10 is not a factor. Then comes the number 11. 7 plus 2 is 9. Alternate digits. And then here alternate digits 4 and 9. 9 minus 11 or 11 minus 9, 2. So 11 is not a factor. 12 is not a factor because 3 and 4 are not factors. Then again 13, we can try 13 also. There are procedures. Or what is the divisibility test by 13? It is there. If you know, you apply. Otherwise, you divide and see. Okay. And then 14, 7 and 2 not there. 14 is not there. Then 15, 5 and 3 not there. Not there. 16 cannot come. And then the next possibility is 17. Let us try whether this number has a factor of 17. Okay. So, yes, it is a factor. It has got a factor of 17. So, we can break this as 17 into, it is multiplying 437 times. Okay. 17 into 437. Many of you have written correctly. And then we have got this number 437. And for 437, what are the factors? 437 again 2, 3, 4, 5. All these numbers we can try one after the other. And finally 19 is a factor for this number. And how many times it multiplies? It is 23 times. Therefore 7429 is a number which can be written as a product of prime numbers as 17 into 19 into 23. Look at these numbers. All the three are prime factors and this is the correct answer. Okay. Many of you have written it. Then let us move on to the third question. Find the HCF of 124, 64 and 72. So here I am going to introduce, we can either you can go by prime factorization method, as it is not mentioned which method to use. So whichever you find easy and convenient, you can use. But if it is mentioned, you have to strictly follow that method only. For 3 numbers, we have to first find the HCF of these 2, and whatever comes as the HCF, and that HCF and the third number, we should try to get the HCF of all the 3 numbers. Okay. So let us take the division lemma only. So 124 can be written as 64 into only one time, and then the plus, it gives you 64, means it is 60 is the remainder. Now this 60 and 64, and then 64 can be written as 60 into one time plus 4. Now this 60 can be written as 4 into 15 times is 60 plus 0 remainder. Therefore, 4 is the HCF of these two. Now here 4 and 72, obviously you all know 4 is a multiple of 72. Sorry, 4 is a factor of 72 or 72 is a multiple of 4 because 18 into 4s we all know 72. Therefore, we can write 4 is also the HCF of 4 and 72. Therefore, 4 is the HCF of these three numbers. We have to conclude like that. Okay. So like that we should do. Okay. Now let us move on to the next question. Here, using prime factorization, find the HCF and LCM of 336 and 54. So 336 and 54, we have to take the two numbers as. So here you are given the method correctly. The method that you have to follow is the prime factorization method. It is given clearly. So we have to adapt to that method only. So now, how do you factorize 336? So 336 is equal to 8 into 42, and then here this 42 is nothing but 14 into 3, and then this 14 is nothing but 2 into 7 into 3, and then 8 is nothing but 2 into 2 into 2. Now you write overall 336 is equal to how many powers of 2 has come? Here 1, 2, 3. So 4 powers of 2 has come, and then 1 power of 7 and 1 power of 3. And this is the factorization of is 336. All the three using fundamental theorem of arithmetic and using factorization method, we have got 336 to be resolved as 2 power 4 into 7 into 3. Now here I would bring it to your kind notice, when you are resolving into prime factors, so it has to be the product of each and every factor that you are identifying should be a prime number. Okay. It should be a prime number. Wonderful. Many of you have written the correct answers. That is fine. So similarly, 54 is nothing but 6 into 9. That is 3 square. And then 6. 6 is again what? 3 into 2. So this is how we can factorize, but 3 has got already what 3 power is there. Therefore, I write 54 as 3 power 3 into 2. So once again, I write 336 as it is nothing but 2 power 4 into 7 into 3, and 54 is written as 3 power 3 into 2. So here, how do we choose the LCM and HCF? This is where many of you go wrong. And now let us take the HCF first. So HCF is common factor. Only 1 power of 3 is common for both these numbers. And then there is only 1 power of 2 is common for both. Okay. Therefore, I write the HCF as 3 2s are 6. Now, how do you choose the LCM as? When we choose the LCM, the highest power you should take 3 to power 4. Apart from this, there is a 3 power 3. So that also the highest power for 3, that also I should take. And then apart from that, 2 and 3 are already included in this. There is one extra factor, that is 7, and that also taken into consideration. Therefore, the product of all the 16 into 27 into 7, finally it comes out to be 3024 is the product, and that is the LCM. So this is how the prime factorization helps us to find the LCM and also the HCF of 2 or 3 numbers. Okay, you have factorization is common, and we have to choose the correct factors with the correct powers in order to find the HCF and LCM. Okay, that's how it is done. Now let us move on to the next question. So these questions are also very common. Verify whether 6 power 5 can end with 0 for any power of for n can end with 0. That is the question. So generally you may come across questions like this in the papers: 6 power n or 4 power n or some number 15 power n. So we have to generalize the case. But here it is a fixed value for n, that is 5 is given. Okay. Now what we can do is, according to that particular statement is very important. So you should write according to the fundamental theorem of arithmetic. According to the fundamental theorem of arithmetic, theorem of arithmetic, this 6 power 5 can be rewritten as 6 can be factorized as 3 into 2, the whole power 5. Now this again we all know by the theory of indices. So this is nothing but 3 into 2 the whole power 5 is nothing but 3 power 5 into 2 power 5. And we all know that 3 power 5 cannot end in 0. How? 3 into 3 into 3 into 3. So 3 threes are 9, 9 threes are 27 into 3, 81 into 3. So that gives you 343. Sorry, 243. And then 2 power 5 is obviously 2 twos are 4 twos are 8 twos are 16 twos are 32. So if you do so, you will get only 3 twos are 6. So the ending digit is going to be 6. So whatever be the product, you don't have to be very much. So this also is not needed. Okay, this is only for you to understand. I have worked out. And then this, if you know very sure that 3 power 5 cannot end in 0, you can just write 3 power 5 cannot end in 0. 2 power 5 also cannot end in 0. So this has got a pattern, this has got a pattern. Therefore, the product cannot end in 0. Okay. So we can write like this. Therefore, the product 3 twos are 5, 3 2 raised to the power 5 also cannot end in 0 for this value 5. Okay, so we have to restrict your answer right like this. So when you find this, the understanding is okay, but when you write this, the answer has to be written like this. 3 power 5 cannot end in 0. Similarly, 2 power 5 cannot end in 0. Therefore, the product 3 power 5 into 2 power 5 cannot end in 0. We have to write. Cannot end in 0. So this is nothing but, therefore 6 power 5 cannot end in 0. We have to write the answer statement in this manner. Okay. We'll move on to the next question. Prove that root 3 is an irrational number. So this is the method which is a very, very early method by the finder of this particular concept that irrational numbers do exist. So this is one particular statement which has been the how to prove this. There is it was proved by a mathematician called Hipposus in the year 300 BC, 320 BC. So we are still following this method only. Okay. Now this method is called the method of contradiction. If root 3 it cannot admit that to be an irrational number, so what is the next possibility? So let us take this as a rational number. If you take this as a rational number and then you have to introduce the term by the method of contradiction. This is very, very important. So by the method of contradiction, let it be a rational number, and therefore it has to have a rational number of the form a by b, where a and b do not have a, that is the proper representation, isn't it? A and b cannot have a common factor, and then b is not equal to 0. So that is the common fact when you are writing it as a rational number. So there are two assumptions that a and b will not have a common factor. Assumption number one. Okay, there that a rational number such that a and b do not have common factor. Yeah, many of you have written it is an irrational number. So that we have to prove, conceptual proof we have to give. Wonderful. So suppose if root 3 is equal to, root 3 is equal to a by b means a is equal to what? Root 3 times b. So if a is equal to root 3 times b means a square, if you square it, that becomes 3b, which proves that a square is a multiple of 3. Okay, 3 times the number means if a square is a multiple of 3, obviously a is also a multiple of 3, and therefore we can write a is equal to some multiple of 3. We are introducing a third integer c. Okay, therefore what do you get? You will get a is equal to 3 times a number c, and a square is equal to 3b. Therefore we will get a, okay, so a square is equal to 9c square. We will get 9c square. Okay, so a square equal to 9c square you will get. So here this 3b is equal to 9c square. So we can write it. So now what is happening? A square is also equal to 3b. A square is also equal to 9c square. Therefore, from this we have concluded that a has got a common factor of 3, and also this, one second. Okay, we can write like this. But a is equal to root 3 times b means, what do you get? A is root 3b must be equal to 3 times of c. Okay, therefore I get 3b is equal to, that is by squaring it, 3b square is equal to, squaring it you will get 9c square. Therefore, b square is equal to 3c square. Therefore, I get b, or b square is written as a multiple of 3 and c square means b also has got a, b square has got a factor of c. Therefore, I get b also has got a common factor of 3. Also has a factor of 3. Common factor 3. So now here our assumption is what? A and B do not have a common factor. From this statement 1, we have got A has got a common factor of 3. From this statement, we have got a common factor B as 3. Therefore, A and B both have a common factor of 3. Therefore, this is this is against the assumption that A and B do not have a common factor. Therefore, our assumption is wrong. What is our assumption? That A and B, root 3 is a rational number, is our assumption. So the assumption is wrong. Here we have said they do not have a common factor. But when we are actually proceeding on these lines, we get A has a common factor, B has also a factor of 3. Therefore, I get our assumption is wrong. Therefore, the root 3 cannot be a rational number. It has to be irrational. This is how we can prove. For understanding this better, you can the same proof has to be written for all such questions like this. Root 5, you can try root 7, root 11, 3 root 11, any number we can take like this. For all these questions, the same answer we have to try with different numbers. Now the next question is 5 plus 3 root 5. And here the question says that it is an irrational number. Whenever this question comes as a 2 marks question, 3 marks question, we always take root 5 as an irrational number only. Here you don't have to prove that root 5 is an irrational number and proceed, not necessary. Again, the method of contradiction works here. Let it be some A and B is equal to A and B, where A and B do not have common factors and they are integers, positive integers. So therefore, what do you get? 3 root 5 is equal to A by B minus 5. So on simplification, you will get A minus 5B by B. Therefore, we get root 5 is equal to, you will get the 3 has to come down, is equal, root 5 is equal to A minus 5B divided by 3B. Therefore, here A is an integer, 5 is an integer, B is an integer. This fraction is a rational number. If this is a rational number, but root 5 is an irrational number, which is a contradiction. Therefore, our assumption is wrong. Therefore, 5 plus root 3, 5 should have to be an irrational number. We should end like this. Okay. Therefore, it is an irrational number we have proved. Next, prove that the product of three numbers is not equal to the product of their LCM and HCF. So it is a proven fact that the LCM of HCF of any two numbers is equal to the product of the numbers. Let me take the numbers just to understand. You take the LCM of 4 and one more number you can take. Say, for example, we'll have 4 and 28, say. So obviously the LCM is 4 here, and then LCM is 28 here, and then HCF is 4 here. Now multiply these two, you will get 112. The numbers you get the product, it is 1, 2. So the product of two numbers is equal to the product of LCM and HCF. We can try any number you want. Okay. So this is one particular, here I have taken to be the multiple just for easier calculations. You can take any numbers, 4 and 15 you can take. So if you take the 4 and 15 numbers, again the LCM is going to be 60. And then HCF is 1. Therefore, 60 into 1 is equal to 15 into 4, that is 60. So this is a proven fact. And then this particular fact is true only for two numbers, not for three numbers. So here he has given that we have to prove the fact that they are not, it is not true. Take the numbers as 672 and 120. Now, if you take these three numbers, obviously the HCF is going to be, I am not going to elaborate because 12 6 is a 26, 6 ones. Therefore, 6 is going to be the common factor. HCF is equal to 6. Okay. If you take the LCM, so what is the LCM here? It is 6 is equal to, if you take 6 is equal to 3 into 2, 72 is equal to 24 into 3 or 12 into 6, 24 into 3, 8 nines are, so therefore 2 power 3 into 3 square we can take, 9, and then here 8. Okay, 120 is nothing but it is 120, if you split it is 40 into 3 or 20 into 6, or anyway you can take it as 60 into 2. Then it is 20 into 3, or split it, it is 10 into 6. So 5 into 2 into 3 into 2 into 2. So you will get 2 power 3 into 3 into 5. Okay. Now, if you take the LCM, what could be the LCM of these three numbers? 2, the highest power is 3. So, 2 cube into. And then here for 3, what is the highest power? Square. So, it is 3 square. And then in addition to that, there is one number that is 5. So, 8 into 9 into 5. 72 into 5. That is 360 is the LCM of these three numbers. Okay, so we have got the HCF of these three numbers as 6, and then LCM of these three numbers is 360, and therefore if you multiply you will get 2160. Now you multiply the number 6 into 72 into 120. So obviously this is not equal to 2160. So therefore we have verified the fact. Okay. This is a very simple question. You can always attempt it easily. Okay. Verify whether the following fractions have terminating or non-terminating decimals. 17 by 80 for sum. So this 17 and 80 can be factorized as 2 into 5 into 2 5s are 10, and then 10 into 8, that is 2 power 3. So it is 17 divided by 2 power 4 into 5. It has got only some 4 powers of 2 as factors, and then and 5, and there is nothing else, no other prime number. Therefore, the decimal expansion is going to be terminating. You have to conclude like this. So how will you write the answer as? The denominator 80 does not have any other prime factor except 2 and 5. Therefore, it's a terminating decimal expansion. Therefore, we have to write like that. Now, I will leave it to you. I am not going to work out. Now, you have to give your answers. Other sums, you please find out whether 15 by 1600 has a terminating decimal expansion or not. Simply write yes or no. Quick. This is the ninth sum I am trying. 15 by 1600. Does it have a terminating or non-terminating decimal expansion? Yeah. Wonderful. All of you have written. Now, some next is, yes, this is a terminating decimal expansion. Now, what about, and then 7 power 5. So, whether it is terminating or non-terminating, you tell me. Here, terminating or non-terminating. Apart from 2 and 5, it has got 7 also as a factor. Therefore, no. It doesn't have a terminating decimal expansion. Then what about 29 by 343? 343 quick. 7 cube. It doesn't have any other prime factor except 7. That is also, it is not a terminating decimal expansion. We can write no. Very good. We'll move on to the next question. Now, I have already told you the product of the two numbers is given to be 38784. The HCF of two numbers is equal to 4. Find the LCM. You have to just divide and then find out whether it is, what quotient you are getting is the LCM of these two numbers. Can you just tell me what it is? The product of LCM, we can even LCM into HCF is equal to 38784, and that is also the product of the numbers, and the HCF is going to be 4. What is the LCM is the question. You divide by 4, and this is 9 6. Have you got the answer? I'm not going to tell the answer. Yes. Have you got the answer? It is 9696. So therefore the LCM is equal to 9696. Now it is also given that if one of the numbers is 96, find the other number. So 38784 has to be divided by 96. Yeah, many of you have written it correctly. It is 404 is the other number. Wonderful. We'll move on to the next question. Here it is. Find the greatest number consisting of 6 digits exactly divisible by 24, 15 and so the number which is exactly divisible by 24, 15 and 36 is the LCM. And what is the LCM of these three numbers? You should first find out. So what is the LCM of these three numbers? Can you just tell me? If you have found it, if you can find out, I'll give you time for it. You find the LCM and tell me. And yeah, what is the LCM of these three numbers? Whoever has found it correctly, please. Okay, yeah, it's correct. So the first one is, the LCM is 1080. Okay, now this number, first the LCM you should find out, and then it has to be, after the LCM is 1080, is obviously not having 6 digits. So we have to find out a particular multiple of 1080, which is also the divisible by 24, 15, and 36, and is having 6 digits. So that is the question. Okay. So how do you do that? So for that, we have to try the greatest number of 6 digits, and then we should try to divide by 1080. So if you divide this by 1080, you get the quotient like this. So many of you have given this number. So it is 2 times. So that particular number is 999 numbers more than that particular number. So what we have to do, we have to subtract from this number and then test whether that number is the correct number we want. Okay. So how do you do that? It is subtract this 999 from this number. Now, this number you tried with 1080 and just check how many times we can divide by this number. So, some of you have given some answers. So, let me check once again. Your answer is right. So, this number you take and then 99900 and divide by 925. So, this is the number that we want. Okay. Okay. Next, there is a circular path around a sports field. Anju takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same time. They will, at what time they will come in the same direction? After how many minutes will they meet again at the at the starting point? So every 12 minutes, one person is going around like this, and the other person starts for every 18th minute. So like this, like this, like this, but the LCM number of times. Okay, so when they come together only when that particular spot is a LCM of these two. So every 12 minutes they come to this place, and then there will be some place they both will reach the same spot, which is happening to, which is nothing but the LCM. Okay, so it is 18 54 like that. If you, we have to find the LCM of 12 and 18. So LCM of 12 and 18 is, it is going to be, find out. So it is 36. So after 3 lapses, they both, and for him 2 lapses. So at the 36th minute, so they will all be at the same, meeting at the same point. So you should conclude like that. Okay. So the next question, show that one and only out of n plus 4 and n plus 12 and n plus 16 is divisible by 5 when n is any positive integer. Any number can be written in the form 2n plus r, okay? Or it is a multiple divisible by 5. So I will choose the number 5. So when any number can be written as 5 times some quotient plus r, where r is equal to, r can take the value 0, 1, 2, 3 and 4 as per division lemma. Okay. So now if we take when r is equal to, so we have to analyze various cases. So case 1, when r equal to 0, it is obviously a multiple of 5. Tick. When r is 1, obviously where it is not divisible by. Okay. Next is n plus 8. When n is equal to 5q plus r means, so we'll get n plus 8. So it is 5q plus r, okay, plus 8. So this is n and this is 8 means, now r is taking the value 1. Therefore, it is 5q plus 1 plus 8, it is 9. So I will get 5q plus 9, which can be broken as 5q plus 5 plus 4. So this together a multiple of 5, and then 4, it is obviously not a multiple of 5. And then next case we can analyze by taking n plus 12. So n is equal to 5q plus 12 and 5q plus r, and then we have to take the value 12 because n plus 12. So n plus 12 is equal to 5q plus r plus 12. Here r is going to take the value 2. So if r is taking the value 2, what do you get? You will get 5q plus 14. So this 14 can be broken as, it is 10 plus 4. Okay, 10 plus 4. So this is a multiple of 5, this is a multiple of 5. So this obviously n plus 12 is not divisible by, so it is not divisible, not divisible by 5. Okay. And similarly, n plus 16 we should take. So in order to take n plus 16 when n is equal to 5q plus r, now here the next case is n is equal to 5q plus r is going to take the value 4, and then it is 16. So it is 5q plus 5q plus 20. So obviously this is a multiple of 5. Therefore, the full number is a multiple of 5. Therefore, when n is equal to, the number is equal to n plus 16, it is divisible by 5. So like that, we have to analyze for various cases taking r is equal to 0, 1, 2, 3 for each and every number separately and prove this concept. And the same thing, 14, I would like you to try as homework, in which we have got a square of an odd positive integer can be of the form 6q plus 1 and 6q. Any square of an odd number can be reducible to this form. That's what you have to prove. Okay. Now, this question I leave it to you for homework. You please try that. Otherwise, we will solve it in the next class if time permits. And now here would request to cover the proof of irrationality of pi. Okay. Now, pi is a number. We all take this as 22 by 7. So going by the definition of pi pi is a constant value. And when do we come across this constant value means when the circumference of a circle is found out and then that is divided by the denominator of the same circle, they always tend to be a particular value, and that particular value is found out to be 3.14, and this is an approximation. Okay, this is an approximation. Therefore, it is only going to tend to this particular value. So that proves that this is not the exact value. So if you convert this decimal after approximation, it is not 3.14 exactly. It is tend to become a value like that. It is by, okay. So maybe after 2, 3, and then we approximate it to 3.14, and we found out this value to be 22 by 7. Or you can even divide this value 22 by 7. You will get 3.12, and then keeping a decimal 17, it is 50, and then it is that is, it is 3, so 4 times, so it is after 6 places it will repeat. Let me find out what exact is the decimal value. See, if you keep on dividing like this, so 3.412857, again 142857, 14 going to repeat. So here we can, that approximated value itself is another approximation. Therefore, it is not certainly the same value as 22 by 7, which is an approximated value. Therefore, 5 is not as a rational number. It is taken to be an irrational number. So this is the, so we can just write in 2 sentences like this, as pi is an approximated value for the constant value which appears when the circumference of a circle is divided by the denominator. So this approximated value is again approximated to the fraction 22 by 7. Pi is not 3.14 or 22 by 7 is not the exact value of pi. Therefore, it is taken to be an irrational number. We have to conclude like this, and already it is time up, and you have got maybe some other classes also. So with that, I conclude this class. Thank you very much for staying with me and participating with me equally, and you are answering the questions correctly, and it was very nice to watch you sending the messages and then asking the doubts and then solving the sums. Thank you so much for staying with me once again. So I will return to the studios.